Hello and welcome to Data Science for Everyone. Today we're going to explore the basics of object-oriented programming, also known as OOP. Up until now, we have been writing code in a regular or procedural style. That means writing instructions in step-by-step order like a recipe. This approach works well for simple tasks or for data analysis, where we load, examine, and draw conclusions from our data. Procedural thinking feels natural. It's how we usually plan our day. But when you're building large software systems, this approach can fall short. Imagine trying to plan the daily routine for thousands of people individually. It just wouldn't scale. Instead, we need to focus on patterns, how groups of people behave and interact. That's where OOP or object-oriented programming comes in. It's about organizing code around objects and the ways they interact, just like users clicking through parts of an app or website. This way of thinking is essential for building complex systems like Python packages. It helps structure our code so it's easier to understand, reuse, and maintain. What are objects? An object is a package that combines both data and functionality. Think of a bank account object. It stores details like name and email and also include actions like deposit or withdraw money. The data inside the object is called its state. The actions it can perform are known as its behavior. In object-oriented programming, state and behavior aren't treated separately. They're grouped together. So instead of managing the account holder data and the actions as different parts, we treat them as one complete unit. In Python, everything is an object. Numbers, strings, booleans, functions, and even pandas data frames are objects. But how are objects created? This brings us to the core concept of object-oriented programming, which are classes. A class acts like a blueprint for creating objects. It defines the possible states, such as attributes like name and email address, and behaviors such as deposit or withdraw money. For instance, the account holder object are instantiated from the account holder class. By defining these attributes and behaviors within the class, we ensure that all account holder objects are consistent and can be treated in a unified way within the program. Classes in Python acts like blueprints. They define a common structure and behavior for all objects of the same type. Take lists, for example. Every list can store items using comma-separated values inside square brackets, and they all share the same methods, like append, insert, or remove to add, insert, and remove items. This consistency comes from the class they are built from. If you ever want to check the class of an object, just use the type function. For instance, running type on a list will confirm that it's a list object. In object-oriented programming, state means the data tied to an object. In Python, we usually store this data in attributes. For instance, every pandas data frame has an attribute called shape, which shows its dimensions, and you can access it using the data frame's name followed by .shape. On the other hand, behavior refers to what an object can do, its functionality. In Python, this is handled through methods. A common example is the .head method, which lets you quickly look at the first 5 rows. You can view all the attributes and methods of an object by using the dir function. For example, if we pass a list to the dir function, we'll see methods like pop and sort listed. The same approach works for classes too. Don't worry about the names with underscores just yet. We'll get into what those means later in the video. Let's dive into object-oriented programming by defining a new class. To define a new class in Python, we use the class keyword, give it a name, and end the line with a colon. The code that follows should be indented. This indentation tells Python what belongs to that class. If we want to make a placeholder class with no content yet, we can simply write pass inside the class block. Even though nothing is defined inside, we can still create objects from it by calling the class name with parentheses. Here we are creating an empty employee class object. Now let's add a method within this class. In this example, we are adding a method called identify to the employee class. Methods are just like functions inside a class, and they look almost like regular functions except for one key difference. They always start with a special first parameter called self, followed by any other parameter, in this case name. This method prints out a string called employee name followed by the name. To see it in action, we create a new employee object by calling the class name. Then we call employee.identify and pass in the name we want. Notice something interesting here. In the method definition, name is the second parameter, but when we call method, we only pass in one argument. That's because Python automatically handles self behind the scenes. We don't need to include it when calling the method. So what exactly is self? Remember, a class is just a blueprint. It doesn't represent any specific object until we create one. That's where self comes in. It acts as a placeholder for the actual object that will be eventually created from the class. When we call a method on an object, like employee.identify, behind the scenes, Python is calling employee.identify employee. In other words, the object itself is passed in automatically as a first argument. That's why we don't write self when we call the method. Here we define a method called set_name that takes two arguments, self and new_name. To add an attribute named name to an employee object, we assign the value of new_name to self.name. Since self represents the object itself, using self.name is the same as writing object.name. So when we call set_name, it creates a name attribute on that specific object and sets its value to the value we provided. At first, when we create a new employee object, it doesn't have a name attribute. But once we call set_name, the attribute is added and we can access it using the dot notation like employee.name. With the name attribute in place, we can now make our identify method more efficient and meaningful. Instead of passing a name every time we called identify, we first use the set_name method to store the name directly inside the object. Then, inside identify, we access the stored name using self.name. This approach makes the object responsible for managing its own data, which is a key idea in object-oriented programming. When we create a new employee and call set_name, the name becomes part of the object's state. That means any method like identify can use it without needing any extra information from outside. Now that we have understood the basics of object-oriented programming, let's dive in deep and look at constructors. Remember that methods are functions defined inside a class, and they always take self as their first argument. Attributes are created by assigning values to self.something inside these methods. A more efficient way is to pass the data into the object when you create it, just like when you make a list or a data frame. Python makes this possible with a special method called a constructor. This method runs automatically whenever a new object is created. It must be named __init__. The double underscores at both ends tells Python that it is a constructor. Here we define the __init___ method for the employee class. It takes a name argument in addition to the self argument. Inside this method, we create a name attribute using self.name equals to name. Now we can pass the employee name in parentheses when creating an employee object, resulting in the init method being automatically called and the name attribute assigned. There are two main ways to define attributes in a class. One is by creating them inside any method. When that method is called, the attribute gets added to the object. The other, more recommended way is to define them all at once inside the constructor. It's best to avoid spreading attribute definitions across multiple methods. If someone else reads your class and it's hundreds of lines long, they'll have to dig through the whole thing just to find where each attribute is defined. Putting all attributes in the constructor not only makes your code easier to follow, but also guarantees that every attribute is set up as soon as the object is created. This helps prevent errors from accessing attributes that haven't been defined yet. Overall, it leads to cleaner and more reliable code. We can extend the init method by creating another parameter, employee salary. Inside this method, we create a new attribute called salary and assign it the value of that parameter. This way, both the name and the salary are set up automatically when the object is created. We can now create an employee object by calling employee with both the name and the salary. The init constructor is also an ideal place to assign default values to attributes. For instance, we can set the salary parameter to 0. This means that if we create an employee object without providing a salary, the salary attribute will still be created and will be automatically set to 0. Now that we understand the basics of object-oriented programming, let's quickly go over a few more conventions that will make our code more user-friendly. To name our classes, use camel case, which means that if our class name contains several words, they should be written without underscores and each word should start with a capital letter. For methods and attributes, it's the opposite. Words should be separated by underscores and all lowercase. The name self is a convention. We could use any word for the first variable of a method. It will always be treated as an object reference regardless. However, for consistency, which makes our code easier to understand, we should always use self. Finally, classes allow for docstrings, allowing us to display useful information about our class and objects created from it. Like with custom functions, a docstring for a class must be placed immediately after the line declaring the class. We should use docstrings to make the developers' lives easier. Now let's take a closer look at the classes and objects by first understanding the key ideas behind object-oriented programming. The first principle is encapsulation, which means bundling data and the methods that work on that data together inside a class. Next is inheritance, which lets us create new classes based on existing ones, so we can reuse and build on previous code without starting from scratch. Finally, there is polymorphism, which allows us to interact with different objects using the same interface. In other words, we can work with multiple objects from the same class in a consistent way, even if their internal details differ. We have already been using encapsulation in our classes. Every time we create objects with unique attribute values and call custom methods, that's encapsulation in action. Now, let's take a step further by distinguishing between instance level and class level attributes. Think back to the employee class we worked on. It had attributes like name and salary, and we assigned those values when creating each object. These attributes belong only to specific objects we create. The keyword self inside the method helps us tie those values to a particular instance when it is initialized. But what if we need a piece of data that stays the same for every object of a class? Say we want to define a minimum salary that applies to all employees in the company. That kind of data shouldn't vary from one object to another. In that case, we define it directly in the class body, outside of the init method. This creates what's called a class attribute. Think of it like a shared variable for the whole class. For example, we could define base salary to 1 million. Notice that we don't use self to define this because it doesn't belong to any single object. Also, it's common to write class attributes in all capital letters. To use this value inside the class, we access it using the class name followed by a dot, like employee.base_salary. Then, in the init method, we can check if the given salary is higher than the minimum. If it is, we use it. If not, we fall back to the base salary. The base salary variable will be shared among all the instances of the employee class. We can access it like any other attribute from the object instance, and the value will be the same across all instances. Here we print the base salary attribute from the two employee objects. This approach is an example of encapsulation, where the data and methods are grouped within the same class. Keep in mind, base salary is defined at the class level. So what happens if we change its value for just one object? Let's say we have two employee objects and we set the base salary of the first one to 50 million. When we print the base salary for both employees, we'll notice the change only applies to the first one. That's because modifying a class attribute through an instance doesn't affect the original class level value. Instead, it creates a new instance attribute for the specific object. This behavior is intentional. It prevents changes in one object from unexpectedly affecting all others, which is important for maintaining data integrity. Now that we see how class attributes behave, let's talk about why they are useful. They're great for defining constants that apply to the whole class, like setting boundaries for attributes. Base salary, for instance, helps us prevent unrealistic values. They're also handy for storing shared values like configuration options in something like a database class, so we don't need to repeat the same setup for every instance. There is another kind of method called a class method, which is tied to the class itself rather than any single object. Class methods have a limited scope since they can't access instance-specific data. To create one, we use the addClass method decorator. Think of a decorator as a way to change how a function behaves. Since methods are functions inside classes, the class method decorator changes the behavior of the method that follows it. When defining a class method, the main difference is the first parameter. It's CLS instead of self. Just like self refers to an instance, CLS refers to the class. After that, you write the method like any other function. But remember, you can't access any instance attributes inside it. To call a class method, we use the class name followed by the method, like classname.method, instead of calling it on an object. Also keep in mind that CLS is just a naming convention. You could technically use any name, but it's best to stick with CLS for clarity. So why do we need class methods? One key reason is to create alternative constructors. Since a class can only have one init method, class methods lets us define other ways to create objects. For example, imagine we want to create an employee object using data stored in a file. We can't use a regular method here because those require an existing instance, and at this point, there isn't one yet. So we write a class method called importFile that takes a file name as input. This method reads the file, where the first line contains the employee name and the second line their salary, and then returns a new employee object. In the return statement, we use the CLS variable, which refers to the class itself. This means it calls the init constructor just like writing employee outside the class would. Then we call the employee.import file by using the class.method syntax, which will create an employee object without explicitly calling the constructor. The file only contains the name and the salary, so these values are assigned to the employee's object attributes. Now that we have covered the basics of classes and instances, let's dive into the core idea of object-oriented programming, which is reusing code. With so many developers out there, chances are that someone has already written a solution to the problem you're working on. You do not want to rewrite the same logic, and instead it is better to use their code. Also, it is not just using other people's code. We often reuse our own code as well. We do not want to repeat something that is already written and tested. That's where inheritance comes in. Inheritance lets us create a new class that automatically includes the features of an existing code so that we don't have to write the same logic again. This makes it easy to expand and add new functionality. Let's say we have created a bank account class with a balance attribute and a withdraw method. The bank handles different types of accounts. For instance, a savings account might have an additional interest rate and a method to calculate interest. But it still shares common features like the balance and the ability to withdraw funds. By letting the savings account inherit from bank account, we can reuse the existing code for those shared features. Similarly, we might have a checking account which also deals with balances and withdrawals, but with a small change. It adds a fee to each withdrawal. Using inheritance, we can tweak the withdraw method to apply the fee and then call the original method from bank account, avoiding the need to rewrite the whole thing. Here is our bank account class that we have defined. So how do we create a savings account class that inherits from it? We start by defining a new class called savings account, but this time we put the parent class name inside parentheses right after the savings account's class's name. If we just use the pass statement inside the savings account class, savings account will automatically have all the features and methods of the bank account class. In this setup, bank account is called the parent class and savings account is called the child class because it inherits from the parent. We can test how this works in practice. Let's create an object from the savings account class. Even though we haven't written a constructor for it ourselves, we are still able to access the balance attribute and call the withdraw method on it. That's because the features come from the parent bank account class. This is a great example of inheritance in action, and it also shows polymorphism, where different classes can be used to the same interface, making our code more flexible and consistent. That works because an object of a child class is also considered an object of its parent class. We can check this by using isInstance on the savings account object. Python will confirm that it's both a savings account and a bank account. But the reverse isn't true. A regular bank account object isn't an instance of the savings account. Now that we have seen how to create an empty child class, let's take it a step further by adding a constructor to our savings account class. This constructor will take two parameters, one for the balance, just like the bank account class, and another for the interest rate. Inside the constructor, the first thing that we do is call the parent class's init method. We do this using the bank account dot underscore underscore init underscore underscore. This tells Python to run the constructor from the bank account class. We pass in self to that method, which refers to the current savings account object. This works because the child class object is also treated as an instance of the parent class in Python. After that, we can add any extra arguments as we need. It's not mandatory to call the parents' constructor from the child's class, but in practice we usually will because it helps us reuse the parents' setup logic. Now let's create a savings account object. We provide a balance and an interest rate and can access these attributes as usual. Just like with any class, we can add methods to a child class the usual way. These methods can work with data from both the child class and the parent class. For instance, we have added a method called calculateInterest, which calculates the interest earned on the account. This method takes in one argument, n, which is the number of periods. Inside the method, we use self.interest, which comes from the savings account class, the child class. We also use self.balance, which is defined in the bank account class, the parent class. By combining these, the method calculates and returns the interest based on the balance, the interest rate, and the number of periods. To create the checking account class, we start by calling the constructor of the parent class bank account. Then we define two new methods, one for deposits and another for withdrawals. In the withdraw method, we introduce an extra parameter called charge, which represents the additional charge for making withdrawals. Inside the method, we check whether the amount being withdrawn is within the allowed limit, which we set up in the constructor. If it is, we call the parent class's withdraw method, but this time we pass in the total of the amount plus the charge, so both are subtracted from the balance. If the amount exceeds the limit, we simply deny the withdrawal. So instead of rewriting the entire withdraw method from scratch, we build on the parent version and just add our custom logic to it. When we call the withdraw method on the checking account object, it uses the new customized version we defined. But if we call withdraw on the regular bank account, it uses the original version from the parent class. Even though the method name is the same, the version that runs depends on the type of object we are calling it on. This is the core idea of polymorphism. Another key difference is, with a checking account object, we can pass 2 arguments to withdraw. But if we try to do the same with the bank account object, it will throw an error. That's because the bank account class wasn't updated. It still expects the original method format. Technically, this breaks the rules of polymorphism a bit. Since the method signatures are different, the withdraw method in the child class no longer fully matches the one in the parent class. They don't share the same interface anymore. Now let's look at how to compare objects. Since a class acts like a blueprint, you might think that 2 objects with the same attributes would be considered equal. But if we compare them directly, the result is false. That actually makes sense. Even if 2 customers have the same name and account balance, they are still separate objects. If we try to print the customer object, we'll get something like customer object at followed by a string of characters. That's not the data. It's showing the memory location where the object is stored. When Python creates an object, it set aside a block of memory for it. The variable like customer A just holds a reference to that memory. So when we create customer A and customer B, Python gives each of them their own separate space in memory. That's why when we compare them, we are really comparing their memory addresses, not their actual contents. Since they point to different places in the memory, Python says they are not equal. But it doesn't always work that way. Take lists for example. If we create 2 lists with the same values, Python compares their contents, not their memory locations. It sees the data is the same and considers them equal. The same goes for other built-in data types. So how can we get the same behavior with our own custom classes? How do we make Python compare their actual attributes inside the objects instead of their memory locations? To make this kind of comparison work, we can define a special method in our class. We are already familiar with the init constructor, which runs automatically when an object is created. In a similar way, Python has a method called __eq__, which automatically uses when 2 objects of the same class are compared with a double equals to. This method takes 2 arguments, typically named self and other, and it must return either true or false. In this example, we have a customer class with a name and balance attributes. We define our own EQ method to compare those attributes instead of using the default behavior, which just checks if the 2 objects live in the same spot in memory. Now if we create customer objects with the same data and compare them using equals to, Python runs our custom EQ method. Since the attribute values match, the result is true. But if we compare 2 objects with different name, for example, the method returns false, just as we would expect. This is a good start, but there's a catch. What happens if we compare 2 objects from different classes, even if they have the same attributes and values? Without any extra checks, Python might still consider them equal, and that's not what we want. To prevent this, we need to add one more condition to our EQ method. We should check that both objects are instances of the same class. We can do this by comparing their types right inside the method. This way, even if the attribute values match, the comparison will return false if the objects belong to different classes. In Python, every comparison operator has a corresponding method that we can define in our own classes. For example, when we use an exclamation mark followed by an equal sign, Python calls the __ne___ method, which stands for not equal. To change how these comparisons work, we just need to create these methods inside our custom classes. Earlier, we looked at how to change the EQ method in a custom class to compare the attributes and the types of two objects. But what if the second object in the comparison is a subclass of the first? Think back to the bank account and savings account classes we used before. In this example, we have added the EQ methods to both the classes. Let's create one object from each class and compare them. You will see that the EQ method from the child class is the one that gets called, and the comparison returns false since the objects are different. Even if you switch the order of comparison, the outcome doesn't change. Python consistently uses the child class's EQ method. We have covered how to compare objects, but what about printing them? As we saw in the last video, printing a custom class object usually shows its memory address. However, many built-in classes give much clearer inputs. For instance, printing a list reveals the actual items inside it. Since displaying the objects clearly is key in software, let's dive into how we can make this happen for our own custom classes. There are two special methods we can add to a class to create printable versions of an object. The str method runs when we use print or str on an object, while the repr method runs when we use repr or print the object directly in the console without the print function. The key difference is that str gives a user-friendly informal view, whereas repr provides a more detailed developer-focused representation. Ideally, repr should be used to return a string that could recreate the object. For example, when we print a NumPy array, it shows the exact code used to make it. If we only implement one of these methods, it's best to choose the repr method since print will fall back on it if str isn't defined. Let's start with the repr method. We define it to take just one argument, self, and have it return a string. Inside, we use an f string. This means placing f right before the quotes, so we can insert variables inside the curly braces. In this case, we include self.name and self.balance. We put single quotes around self.name to make sure the output looks like a valid code and recreate the object, with the name as a string and the balance as a number. When we create an object and display it, we see the repr output. Since the class doesn't have a str method, calling print on the object will also use the repr method. The str method also only takes self as an argument and returns a string. In this example, the string shows the word customer followed by the customer's name and balance on separate lines. We use triple quotes to create multiple line string and again use an f string that lets us insert the variables easily. Now when we create a customer object and print it, the output is clear and easy to read for the users. Now that we have a solid understanding of object-oriented programming, let's discuss errors and exceptions. Certain Python statements can trigger errors when you run them. For instance, dividing by 0 or trying to combine incompatible types will cause issues. These errors are known as exceptions. Each exception has a specific name, like zero division error or type error as shown here. If these exceptions aren't managed properly, they'll halt your program's execution. Sometimes this is intentional, like when you use a variable that doesn't exist. It signals a serious problem in your code. But in other cases, stopping the program isn't what you want. Sometimes we want our script to keep running even if an error happens, while still recording that error. To do this, we write a special code that handles such cases. We use a try except finally structure to catch and manage exceptions. First, we write try, then put the code that might cause a problem inside it. Let's look at an example that will definitely cause an error, trying to add a number 3 and a string z. Next, we add an except block that specifies the exact exception to catch. In this case, a type error. Inside this except block, we include the code to run if that error occurs, like printing a message. If the error happens, the program won't stop. Instead, it runs the code in the except block. You can also have several except blocks for different exceptions. Finally, there is an optional finally block, which contains the code that always runs no matter what. When we run this example, we see the message from the except block because the error was caught, and we also see the output from the finally block since it runs regardless. There are times when we want to trigger exceptions on purpose, especially if certain conditions are not met. To do this, we use the raise keyword, followed by the exception we want to raise. We can also include a custom error message inside parentheses. Then, whoever uses the code can choose to catch and handle that error with try and except blocks. In Python, exceptions are actually classes that come from built-in base classes like base exception or exception. Here's a quick look at the large hierarchy of the built-in exception classes. For instance, there's a broad category called arithmetic errors, and zero division error is one of the specific types within that group. You can create your own exceptions in Python. Custom exceptions are great because they let you handle errors that are specific to your application. To make one, you just define a class that inherits from the built-in exception class or one of its subclasses. The class doesn't need to have any extra code, just inheriting from exception is enough for Python to recognize it as an exception. For example, you could define a class called bank balance error that inherits from exception. Then, inside the customer class, you can raise this bank balance error if someone tries to create a customer with a negative balance. Now, if we attempt to create a customer with a negative account balance, the bank balance error exception is raised. Previously, we dealt with this situation by merely printing a message and then creating an object with zero balance. The person using the code can choose to handle this exception with a try except block if they want, but it's not something we decide for them. For example, here the bank balance error is caught in the except block, and when that happens, the code creates a customer with a zero balance instead. That brings us to an end of the course on object-oriented programming in Python. Don't forget to like, comment, and subscribe to my channel if you liked this video. Thank you.